Welcome to Utah State University's Vertebrate Paleontology course. My name is Benjamin Berger, and in this lecture we will analyze the anatomy of Pterosauria and the group's specializations toward flight. The pterosaurs are one of three groups of vertebrates that took to the air, and I'm going to say something a bit radical. I think the pterosaurs were the best flyers of the three groups, even outmatching birds in terms of their unique features to make them amazing flying animals. Pterosaurs were the first group of vertebrates to conquer the air, and they did it remarkably early during the late Triassic, with the origin of birds 50 million years later and the origin of bats 150 million years later. So the pterosaurs were the first flying vertebrates by a long margin. Pterosaurs are the sister group to dinosaurs, and together in a group called the Ornithodira, which includes animals that exhibit a crocodile reverse ankle joint, and somewhat synonymous with the clade called Avimetatarsalia. They're united by all the archosaur traits, such as serrated teeth in the sockets, large anorbital fenestra, a fourth trochanter on the femur, and a mandibular fenestra. Hence, they're more closely related to crocodiles and birds than they are related to lizards and snakes. The earliest well-preserved pterosaur is Eudimorphodon from the late Triassic of Italy. It features a very advanced anatomy that is already highly specialized for flight. The teeth were long and pointed, indicating that it fed possibly on a diet of fish, as it is found on the margin of a marine coastline. Late Triassic pterosaurs are rare, but they've been found in Europe and North America, indicating they had a global distribution during the late Triassic. The anatomy of pterosaurs is highly adapted toward flight. In the axial skeleton, we see that they exhibit a very large sternum or breastplate that supported strong flight muscles, some belly ribs, and a fusion of the dorsal vertebrae into what is called the notarium. The notarium provides an articulation with the scapula, and this makes the shoulder girdle very rigid. The sacrum is also fused and closely attached to the pelvis. The pelvis features a posterior projecting pubis or prepubis, a narrow ilium and ischium closely articulating with the sacrum, with an opaque or closed acetabulum or hip socket. Some pterosaurs have long tails, while others have short tails. The neck vertebrae are well developed, and there is strong evidence for pneumatic openings, indicating that pterosaurs had an avian style of respiration with an abundance of air sacs, which further lightened their bodies for flight. The forearms are highly specialized to support a wing membrane. The pinky finger, or actually the fourth digit, is highly elongated into a wing support. Claws are found on the first three digits, which still retain the function of gripping, which is useful for scrambling or climbing. This arrangement is unlike birds, who lose their grabbing abilities of the hand completely in the development of the bird wing. At the wrist are a series of carpal bones, as well as a projection of a little bone called the pteroid. The pteroid supported a membrane that ran across the anterior edge of the wing. This bone allowed the flying pterosaurs to have some motion at the edge of the wing, which might have served a similar function as the olua in birds of prey. By adjusting the leading edge of the wing, pterosaurs could generate a vortex of wind that would both increase lift and enhance maneuverability when diving after prey. There's a lot of debate of the position of the pteroid bone, whether it projected forward or sideways to support the edges of the wing. Modeling of the edge wing forces seems to suggest that it lay flat alongside the edge and it helped to support it, but with some maneuverability. The major muscles of flight were highly developed in pterosaurs, with very large supracorticoideus and pectoralis muscles, the same muscles used by birds. But with the supracorticoideus, dorsal to the wing rather than looping through a notch in the humerus as in birds. As such, pterosaurs had both large breast muscles as well as shoulder muscles, whereas birds just have large breast muscles that support the flapping of the wing. These large breast and shoulder muscles provided enough energy to keep pterosaurs flying for long flights and more evenly distributed the weight of the body than you find in modern birds. The flapping of the membrane wings likely provided an abundance of downward force, and the thorough upstroke likely did not involve as much of an inward movement of the wing as in birds. The hind legs featured long legs with a recurved fifth toe that it could use to hang upside down, which is similar to bats. The feet were padded with scales and thick, fleshy pads of keratin, which is similar to what you find in bird feet. Many pterosaurs are covered in fuzzy hair-like integumentary structures. They're similar to those found in dinosaurs. These integumentary structures likely provided insulation to the pterosaurs, and they're found in the smaller members of the group. One of the most bizarre pterosaurs is the frog-mouthed Johoopterus from the early Cretaceous of China. Now, this little pterosaur was covered in fluff, and it had a frog-like mouth that was wide and round, and these little flying creatures likely ate insects like modern bats. The integumentary structures that form the membranes of the wings are really fascinating. In the Jurassic pterosaur sorties, narrow networks of fibers can be seen in the membrane, giving the membrane a support structure. SEM cross-sections of the wing membranes show that the wing fibers were wedged between two layers, an outer mattress layer and an inner muscle layer. The muscle layer would have enabled the flying pterosaur to adjust any of the membrane's surface during flight and give the animal considerable control of the wing surface. Blood vessels fed and nourished these muscles in the membrane during flight with well-oxygenated blood. Pterosaurs have three sets of wing membranes. The membrane along the anterior edge of the arm is called the propterygium. The chiropterygium is the larger membrane that forms the majority of the wing, and the chiropterygium that was between the legs at the end of the pterosaur. In more advanced pterosaurs that lack a long tail, the chiropterygium was less extensive. The bones of pterosaurs are light and hollow, and together with the powerful flight muscles and complex wing membranes, pterosaurs were exceptional flyers. One question was whether they were good landers. Pterosaurs would walk by retracting their fourth digit and folding the chiropterygium under their arms while using both their hands and feet to walk on four legs. This method of walking was highly controversial until trackways of pterosaurs were discovered. Now there's a remarkably great record of tracks left by pterosaurs showing how they would walk on their four legs. There are even some trackways of pterosaurs coming in for a landing where they touched down first with their hind legs and then brought their forearms and hands down with the next step and then moved with their four legs and quickly scampered away. Pterosaurs, like their cousins, the dinosaurs, also lay eggs, and there are some remarkable fossils of pterosaur eggs found with tiny embryos. Some of these eggs are still within the body cavity of the mother. They likely made nests like birds. Pterosaurs lived throughout the late Triassic, the Jurassic, and Cretaceous. Jurassic pterosaurs tend to be grouped in a paraphyletic group called the Rhamphorhynchoids, which tend to be smaller pterosaurs with large heads, sharp teeth, and long tails. Because the term Rhamphorhynchoids is used to group basal members of pterosaurs, it's often not used as often anymore. During the Cretaceous, pterosaurs became very large and more specialized for long-distance flights, and most are found in marine rock units. These include the Pteranodontae, which lacked teeth and had very weird crests on their heads. These crests likely did not help in flying and may have been used for display rather than having any function for flight. The Nyctosauridae are another closely related late Cretaceous pterosaur. The term pterodactyl stems from the first pterosaur discovered, named by George Cuvier as pterodactyl in 1809. And although it pertains to a specific genus, it's often used by the general public as a synonym for all pterosaurs, the pterodactyls. The largest and perhaps most bizarre of the pterosaurs are the Azarachidae family, which lived at the end of the Cretaceous. The group includes the largest pterosaur to have ever lived, the giant Quetzalcoatlus. Now, many people have invoked the idea of a giant flying pterosaur at the very end of the Cretaceous. And Quetzalcoatlus from the late Cretaceous of Texas was a very large member of the group, with a wingspan of between 5 to 10 meters, where the largest living condors have a wingspan of only about 3 meters today. This would make Quetzalcoatlus the largest flying vertebrate. However, Witten and Nash have kind of argued that Quetzalcoatlus might have been flightless and walking instead on all 4 of its legs. This is supported by trackways from Korea and some smaller members of the group that appear to be adapted to walking as much as active flight. These large pterosaurs were some of the last pterosaurs to have lived on Earth. In looking at the evolution of pterosaurs throughout much of their existence during the Cretaceous, they lived alongside flying birds. Birds during the Cretaceous were small, about the size of sparrows, while pterosaurs became the long-distance marine flyers similar to living albatross and various marine gulls, but they're also found in terrestrial environments as well. At the end of the Cretaceous, the pterosaurs, despite their great abilities of having superior flight, died off. And it was the smaller feathered birds that would rise to take their place. All right, be sure to analyze the anatomy of the Pterosauria and the group's specializations toward flight. Many of the figures that I used in this lecture come from a great book by David Ewan called The Pterosaurs from Deep Time, which you should check out if you're interested in learning more about pterosaurs. Another book that I'd recommend is Mark Wheaton's 2013 book called Pterosaurs, Natural History, Evolution, and Anatomy, which is lavishly illustrated with chapters on each group of pterosaurs. Thank you for watching. If you'd like to learn more about Utah State University's geology program, check out the website geology.usu.edu or my own website at benjamin-berger.org. Links are found in the description below.